Of course, if you haven't done so yet, just make sure you pause the video and give the question another try before listening on. In this question, we have a very long non-conducting rod that has a uniform charge density of 6 microcoulombs per meter. So what we've done is drawn a very long non-conducting rod. We've sprinkled some positive charges uniformly all along its length. We know they're positive because the charge density was positive 6 microcoulombs per meter. And then what we're going to do is we're going to take an electron and we're going to release it 9 centimeters from the rod. So we might imagine that we take the electron and we drop it right here. And because the electron is negatively charged, it's going to be electrostatically attracted to that positively charged rod, and it will be attracted by an electric force. So we might label that F with a subscript E to represent the electric force. Now we recall from a previous chapter perhaps that the electric force, or at least the magnitude of the electric force, is equal to the magnitude of the electric field multiplied by the magnitude of charge. Now we don't want the electric force per se, we want the initial acceleration. We would assume that the only relevant force acting on this electron is the electric force. So we actually could say that the net force is equal to the electric field magnitude times the charge magnitude. Now we remember from Newton's second law from Physics 1 that the net force acting on an object is equal to the object's mass multiplied by its acceleration. So we can substitute that in for F net. And then finally, to solve for the acceleration, we can divide both sides of the equation by the mass. They'll cancel out on the left-hand side, and there we go. We have the expression for the acceleration. Now, we know the mass of an electron. We can look that up. We also know the charge of an electron. But what we don't yet have is the electric field magnitude. Now, it turns out that through the use of Gauss's law, that for a very long conducting rod, which is sometimes called a line of charge, the electric field magnitude is given by this expression right here. So what we'll do is we'll take this expression for E and we'll plug it in for E in our equation. So we would have the acceleration equals lambda, we'll talk about that in just a moment, over 2 pi epsilon naught times radius. So there's your electric field multiplied by Q, and then divided by the mass. We may wish to clean this up just a little bit. This term here, 2 pi epsilon r, that's actually going to be able to be shifted to the denominator. There's a long story to that. There's also a short story. If you have a fraction over a whole number, the bottom part of this fraction can be moved to the denominator. So that would give you a over b times c. Just a little mathematical trick. So now we have the lambda, which stays on top, along with q, all divided by 2 pi epsilon naught times r times m. So lambda, this Greek letter right here, is the linear charge density. That's the value they gave us at the beginning of the problem, right there. And then the r is the distance from the rod, and that was given as 9 centimeters. So we're going to begin to plug in all the known values here. We will be a little bit cautious about the units. So for lambda, it was 6 microcoulombs per meter. Yeah, 6 microcoulombs per meter, but it's microcoulombs, so you have to take 6 and then multiply that by 10 to the negative 6. So that would be in coulombs per meter, times the charge on an electron, which is 1.6 times 10 to the negative 19th coulombs. Notice we're just using the positive version of the charge because we just need the magnitude. Divided by 2 pi times epsilon, which is 8.85 times 10 to the minus 12. And then the unit for that is hiding over here, coulombs squared per Newton meters squared. Coulombs squared over Newton meters squared, kind of an ugly unit. And then we have the distance. Now that was 9 centimeters, but we want it in meters, so you have to do 9 times 10 to the minus 2 meters, and then multiplied by the mass of the electron. We're going to need to make some room here. The mass of an electron can be looked up in the back of your textbook, and that is 9.11 times 10 to the minus 31 kilograms. All right, so carefully plug that in your calculator, and you would get about 2.1 times 10 to the power of 17. This is acceleration, so it's meters per second squared. And that would be the electron's initial acceleration when it is released.